Hey, it's Nikita and Abby here, and we're going to help you go through some problems in the textbook. So first off, I have number 47 on page 621. And the question says that a 120 volt air conditioner unit draws 15 amps of current. If it operates for 20 minutes, how much energy in kilowatt hours does it use in that time? If the cost of electricity is 15 cents per kilowatt hour, what is the cost of operating the unit for 20 minutes? And if the air conditioner initially cost $450 and it is operated on average 4 hours per day, how long does it take before the operating cost equals the price? So we have here the 120 volt air conditioner and the current of 15. So power is equal to the current times the potential difference, and by 15 times 120 we get 1800 watts. So that's the power. Then we're going to change that to kilowatts and we get 1.8 kilowatts. We know that 20 minutes is a third of an hour, so kilowatt hour, so 1.8 times 1/3 of an hour is going to give us 0.6 kilowatts per hour. And since the cost is 15 cents per kilowatt hour, we have 0.6 times 0.15 and we get 9 cents. Now we're trying to find the number of hours or days that it takes till it equals $450. So $450 times 0.15 will give us 3,000 kilowatt hours. So I'm going to find out the number of hours it takes for it to equal 3,000 kilowatts per hour. So I have 3,000 kilowatts per hour divided by 1.8 kilowatt, and I get 1,666 hours and 40 minutes, which gives us approximately 417 days till the operating cost equals the price of the air conditioner unit.
Alright, moving on to our next problem. It's number 56. And the problem is, to empty a flooded basement, a water pump must do work at a rate of 2 kilowatt. If the pump is wired to a 240 volt source and is 84% efficient, A, how much current does it draw, and B, what is its resistance? So we basically start out by noting that it's 84% efficient. So basically 84% of what the power that it has, it basically only does it only has 2 kilowatts per 2 kilowatts of power. So if you want to find P, so we take 2 and we divide it by 84%. So we get 2.381 kilowatt. And then using Joule's law, we can use it to say that 2.381, which is the power, is equal to your current I times 240 volts, which is your potential difference. So if we solve for I, we basically get 0.009921 amperes. Then if we go down to Ohm's law, we can use that to say that I equals 1 over R times delta V. So that is 0.009921 amperes is equal to 1 over R, your resistance, times 240 volts, which is your potential difference. So then we go on to say R is equal to 24,191.52 ohms. And that's that problem.
So recently I went to India 2 weeks ago, and over there I took my hair dryer. And I used my hair dryer and I put it on the 125 volt setting, and I plugged it into India's 220 volt power source. It ran for 5 seconds, overheated, and stopped working. After that, we thought it was broken. So basically, we're gonna talk about how dangerous it is. So the hair dryer is 1,875 watts, and using the law, we find out that the current in the 220 volt power source in India is 8.52 amps, which means it's really deadly. And in America, since it's 120 volts, we find that the current is 15.63 amps, which is even more deadly.
Yeah, and also I'd like to add that the reason that it overheated was because since it was on the 125 setting and we put it in a 220 volt source, basically it had the potential difference was too great for it, and it overheated, which caused some smoke as well. So
thank you for listening, and we hope you learned stuff. Bye.
Off.